Hello everyone. Today I'm gonna be doing another example of linear programming, and it's here. This is basically, you can just stop the video and to read this, and just basically this is an airplane which has 3 compartments from center and rear, and we want to distribute 4 kind of cargo into these 3 compartments in the airplane, and we have a limit in the available weight of the airplane of each compartment, and we have also excuse me, this is the available weight of each cargo, and this is the capacity for the compartment measured in weight. And this is the also capacity of the compartment, but this is referred to the volume. Okay, so we have 2 kind of capacity for the compartment: volume and weight. And finally, the last constraint here is to maintain the airplane balanced. So we need to have the same amount of we need to have the same weight throughout each compartment. Okay, so I'm just gonna follow formulation, and I already have here the class that I'm gonna be using to solve the problem. And let's just start. Okay, so I'm gonna name the method public static void. Okay, so this is just gonna be we're gonna have all the code, and I'm gonna use this variable I already have in here on the clipboard. So we have n, the number of different cargos we have, the 3 compartments in M, and I define all of the parameters we need. B is going to be the profit per cargo, which is here, profit per cargo. Lowercase v is going to be the volume per ton of each cargo, which is this one here. A, the available weight for each cargo. And so, I mean, as you can see, we might not ship everything, so that's possible. So, but we want to ship as much as possible so that we maximize our profit. And capital V is going to be the available amount of volume space of each compartment. Okay. All right. Okay, so now I'm gonna try and define the model. We're gonna define the model. Define the model. All right, let's say CPLEX equal new CPLEX. Okay. And there's an exception here that I have to write. So catch. It's gonna be exception. Exception. And I'm missing something here. Catch there. So it's going to be print stack trace. Okay, so this is only to print in the console whatever error might occur. Okay. And what's going on here? There's no dot. Okay, good. Let's continue now. Let's define the variables. This is new, the new thing. So variables. Okay, so as we saw before, this is island bar, but now this is a 2-index variable, so I'm gonna make it a matrix. There you go. It's gonna be x. This is gonna be a new island bar. So we define the first part of the matrix, which is size n. Remember, xij is going to be I stands for cargo, so we have 4 cargos, n is 4, and j, which is going to be the compartment, that's m. Okay, but we'll see when we're going to use that. We don't put it there. So you always the last dimension you can always leave it blank because you can define it later. And we're going to see right now how. Okay, so for each of the cargo, so we're going to iterate through each cargo type. And we're going to define the last dimension of the matrix. Okay, we need to do it in some other way. So just gonna write it and then explain it. So CPLEX. Okay, so here you're really doing the the declaration of the variable. So for each type of cargo, I'm going to define an array of variables. So at this level is the m. It has to be of m size. And now we put the range of the variable. So in this case, we know that variables are equal or greater than 0. So from 0 to infinite. And infinite here, you write it like this. That's it. There we have our x variable. And we have here a y variable. So in that case, we can just, this is one dimension only, so you can just write this CPLEX number. This is just 1. It goes from 0 to infinity. Okay. Good. Okay, let's define some expressions now before going ahead and write the constraints. So let's just define some expressions what you're going to be using for that. So for the first one, there's nothing to be written. Let's see. Linear norm expression. So basically we're going to have a function that's going to be defined the summation of all of these x for each I, in order to know how much weight we're using. Okay, so we're going to call this used weight capacity. So this is a new expression of size m. And the same for the volume. So this is going to indicate how much weight we have on each compartment and how much volume we've been using in each compartment. All right, so we write this is going to be for each compartment, so we're going to use J. For each compartment, and then so the first one. Okay, now we need to create it in the model. Okay, so here you just create the variable, but here you associate it with the model. And this is, there's something wrong here. This is no expression. What am I doing wrong here? Okay, so I wrote okay, let's just make sure. Oh, okay. I forgot to put here there we go. So it's for each one. And we do the same for the volume. All right. So we continue here. So now we're gonna actually create the expression, because so far each expression it doesn't have anything. So for the use with, so for each compartment, the expression is going to be, you're going to add term 1.0 x I. Yeah. Okay, so what's happening here is that for each compartment, we are adding up, because J here stays constant. After this declaration, J remains constant, and then we iterate through all of the i's and make a summation. So each of these expressions is going to have the summation of the xij's. And for the volume, we need to transform, instead of multiplying by 1, we would need to multiply by v. So in this case, we use this one, which is the volume per ton of cargo I. there. Okay, and let's make one more expression for the objective. Okay, so this is not a matrix, so we just go ahead, CPLEX linear expression. There. Let's define it. So for each cargo, that is assigned to each compartment. Okay, has to stay below M. We say that the objective is going to be a summation of the profit multiply by the variable. Okay, there we go. Okay, so there we have our expressions. Let's build a model now. So our objective will be maximize, and we already have the objective here defined, so we just write it like that. Maximize the objective, and now constraints. Okay, so first constraint. Let's define first constraint. So the amount of weight to be chipped cannot be bigger than the amount available. That's, of course. So we'll just write that up. So for each cargo, for each type of cargo, all right, so for each type of cargo, we add CPLEX add less than equal. All right, let's pay attention here. This is going to be the summation of x I has to be less than equal to a I. All right, this is interesting. What we're doing here is that we didn't write the whole thing. I mean, for each of the terms in the matrix. I mean, okay. So what am I saying? So usually this is the variable xij, right? So here we're writing CPLEX is gonna make the summation of the xi. So for each xi, you have mx. So basically here what it's doing is that for example, the first one, when I is 0, the CPLEX sum x0 is gonna sum x0, x00, x01, and x02. Okay, it goes from 0 to 2 because we only have 3 compartments. So that's what it's doing. Okay, that's what it's doing. And in this case, this number would be just a constant. Okay, so this is very convenient because we don't have to iterate through the j's as well. So we only iterate through the i's, and then CPLEX takes care of the summation. All right, so that was constraint 1. Let's do the other constraints. All right, so for this case, we're doing the second one. Is for the weight capacity. So this is the case going to be CPLEX dot not less than equal. And this is why we define this here. Use capacity for J. Used waste capacity for compartment A has to be less than equal than the available capacity Cj. So in this case, it would be C. Yeah. All right. And since we are already iterating through the J's, you can see here these 3 constraints. It is for each J, so we're just going to write all of the constraints here. We have then, this is the third one, at less than equal. What do we have here? The volume. So the volume, use volume, J has to be less than equal than the available volume, which is capital V J. And the last constraint for the to maintain the airplane balanced, in this case is an equal. It's a constraint with an equal there. So we're gonna write CPLEX product. The product is over 1 divided by Cj, the constant. Is 1 divided by Cj multiplied by the summation of the x over the i's, which is represented by the use weight capacity. So we're just gonna take this from here and use weight capacity there, and this has to be the same for all compartments. So basically, this represents the fraction of the weight capacity of each compartment. So the proportion of weight on each compartment has to be the same. Okay, so that's how you maintain the airplane balanced. And that's it with the constraints. So let's just solve the problem now. Solve the problem. So we're gonna write if CPLEX.solve. So if we get a solution, let's go simple here. I'm just gonna write the objective function. So the objective is equal to, just gonna put here the objective get objective value. Okay, if it doesn't get solved, just gonna write, what am I missing here? Print out. Okay, so, and I'm gonna bring from example 1 the display option to not show. So simply doesn't show anything. We have to do it before solving it. This is to mute whatever CPLEX wants to print. You can change this parameter as you like. But if you don't want anything for CPLEX to display, you have to put this every time. And don't forget, after solving this, you should always close CPLEX. Close this and there. All right. Let's save this. There's no error. And we need to go back here to the application. We were solving example 1. Let's change it for 2 now. And there we go. So the objective function is 12,000 and so something. All right, so that's it for today. I'll try to come back in no more than 1 week to some other example. Okay, thank you for your attention.